So little mechanical engineering exposure we have for the equipment design for food processing. Maybe that possible I will may touch in or may not be also, because this is only for biomedical is the charter that was given by our organizer.
Even though they are from mechanical, they are all working in biomedical.
That's right. So interdisciplinary. That is the first criteria that we have for this. Yeah. So this is the place I have been working for long. Now this is the recently he said, but time flies. Already it is 2 years over since I joined here. So this is the work I carried out at CFTRI, product development, process development, dehydration, especially we look at the mass transfer and modeling aspects. Drying, food material drying is very difficult. That's why we use field assisted drying to increase the mass transfer. So heat transfer, mass transfer for the analysis for the equipment of traditional foods. That's where we had a commonality with it. A design of bioreactors for solid state and submerged fermentation, tray, pack, rotary, integrated.
We will provide you students, sir. Then we will.
No problem. Right. So bioreactors for acoustics, heavy root cultures and plant cell cultures, they are very heat sensitive and shear sensitive. For them, special reactors we designed. Now that work we are continuing even at IIT Tirupati. So that now at the moment I have already 5 PhD students and 3 more will be joining this session. And downstream processing is one area we have been strongly have been worked and now continuing that work here. So I present a few case studies for your consumption. If that excites you, any of you to pursue that, the purpose of this course as well as this talk, I will consider it is fulfilled. So as I titled my talk, it is about biomolecules and sensors for biomedical applications. So these are the biomolecules which have a lot of application. So as I mentioned, downstream processing is how you isolate the product from the fermentation broth. So most of the people assumed world over that if you produce, no big deal, you can do the downstream processing, you can get the product, which is not true. It's a very, very wrong assumption even till today. So sometimes 80 to 90% of the product cost goes for downstream processing. So that's where the issue lies. So several unit operations you will be using, but still the product purity is not easy to achieve without compromising on the yield. So that's why we have one of the groups we take. Scenario is no different even in India. So that's why we have taken up that. You know the name also. Suppose if you take fermentation as the center hard, so whatever you do before fermentation is upstream, whatever you do afterwards for isolation of the product and purification is downstream processing. Series of steps are required to do that. So it's almost a downstream processing is a train of unit operations that you cover. So each step may be very efficient. Per se, each step is 90% or above efficiency is there. But I need at least say 5 or 6 steps. So after second step, overall efficiency is 90 into 90, 80. After third step, 80 into 90, 70. Fourth step, 60. Fifth step, 50. So if I cross 5 series of steps, so it goes below the economic viability of the process. That's where the problem lies. But why it is so difficult? Difficult because my biomolecule is present in very low concentration and it is present along with so many other unwanted things. See, for example, if I am isolating a protein A, protein B is also contaminant with respect to A, even though it can be a product independently. But with reference to this, that is impurity. So that's where the issue came. So we have to optimize our yield without compromising on the purity. Aqueous two-phase extraction is one of the environmentally friendly technique that we have actively pursued for several things. Entire downstream processing I cannot cover. It leads entire course I have to take series of lectures. It is not feasible and not required also. I concentrate taking example of case study of one unit operation called extraction. I do not know, some of at least biomedical people must be exposed to organic aqueous extraction from herbs, spices, active principles will extract. So conventionally for biomolecules like proteins, enzymes, natural colors, this kind of things, conventional extraction of organic aqueous will not work for two reasons. One is organic phase denaturizes the product. Second is the solubility of this biomolecule is low in organic solvents. So that's where the issue lies. So there was a aqueous two-phase extraction, there was a need. Aqueous two-phase extraction is really sort of a close to marvel to see that both phases contains 85 to 90% water, but still they exist as a two separate phases. So that's where the beauty lies. It was observed by almost 100 years ago, but gained importance only very recently. The main advantage is it has a high capacity, biocompatible environment. So because high moisture content is there, 80 to 90% is water. So then low interfacial tension. Yeah, any issue, any time now, please interrupt. You do not have to wait till the end of the talk or something. Low interfacial tension, because water is more, so interfacial tension is more, orders of magnitude lower compared to organic aqueous extraction. Then what is the advantage of having a low interfacial tension? Master answer is very easy. Simply I shake it, it will disperse. So mixing is easy. Resistance for the interface mass transfer is very low. So, but that is the best part. But what is the price that I will pay? The price I pay is each phase will disperse into other phase so well, it leads to formation of emulsion. So, phase separation after the extraction is an issue which we will be talking. So, each advantage will have other disadvantage which we have to address. So since it is easy to mix, high yields and low process time, energy is not required, easy to mix, so low energy and ease of scale up. So even you are also aware of a scale up. This word is common for anybody. Scale up is not just for cooking 2 people and cooking 100 people is not the scale up. The point in scale up is to maintain the same productivity in the lab process also at a larger scale. That means I am eliminating the effect of scale. So that is the scale up. That is the real challenge. And scope for continuous operation. Any day, continuous process is have a higher productivity compared to batch process. So this has a provision which can be extendable to continuous process. Automatically productivity will increase. But there are certain criticisms about ATP in the literature. They say that it is not very selective. Selectivity is low to extract the target biomolecule. And it is not true. We ourselves, I will show you some of the case studies. By using a single step ATP, we achieved very high quantities. That means how well you design your experiment, how well you design your parameters. So it depends on that ability. You have to play around with the parameters and optimize them to get the best of the results. But why do they form? What is this aqueous two-phase system? Why do they form? Any solute, if you water soluble solute, if you take and put it water, it comfortably goes into solution, that we know. But when two things, when you dissolve them, after certain concentration, they fight for water and separate into two phases. That means the Gibbs free energy of mixing falls lower than the interaction energy of the material with water. So why that happens only for polymer? Because polymer has a long chain length. So that's why the interaction energy is much higher. So even if suppose you put a salt and sugar also, it should happen, it will happen. But I have to reach a concentration of 40 weight by weight or something. That level, that high concentration of salt and sugar is detrimental, viscosity will be more. Salt concentration will denature my biomolecule, so it won't serve my purpose. That's why I go for, they started with polymer. So, but polymer has a issue, cost of the material is very high. Then they switched over to polymer salt, and another advantage is I need not reinvent the wheel. Whatever is the equipment that is already in the chemical process industry, mechanical agitators, spray columns, packed columns, all this equipment I can use directly for aqueous two-phase extraction without looking for a development of a new equipment. But I can modify them, which I will be share with you to meet my requirement. This is the typical phase diagram. As I mentioned to you, it will be in the cursor visible, yeah. So this is my one phase region, because at these concentrations, both the polymer as well, polymer or salt. So bottom phase can be salt also. So I'll give you examples what are the molecules. So when they put them, until this certain critical concentration, they are comfortable in the solution. I cross this critical concentration, I will enter the two-phase region. Any point on this tie line will split into two phases, top phase and bottom phase. This top phase will be enriched in PEG concentration, and bottom phase will be enriched in another phase. So that means, take a typical example of A1, this is 20 and 25. Whereas in the top phase now, I have about 35 plus PEG and very low value of salt, say 15. Coming to bottom phase, I have very low value of PEG, say 7 or 5, and my salt has increased to 32, even though I started with 20 and 25 at this point. So enrichment will take place. They split into, one is predominantly top phase and one is predominantly containing other polymer or salt in the bottom phase. So this is where the phase separation occurs and facilitates. Another thing I draw your attention is, on any tie line, if I have any tie line, suppose I take this tie line, any point on this tie line will give the same composition of the top and bottom phases. That is the best part of it. That is the thermodynamics decided. It is true even for liquid-liquid extraction, conventional liquid-liquid extraction. So then there must be some difference. If all the points are giving, so there must be some difference of location of this location and this location. What is the difference? The difference is, even though they have the same composition, the volume ratio is different. So that is where I will exploit it. For example, if I am here, it is an inverse arm rule. So now, when I am here, my volume of the top phase is proportional to this length. That's why I have a large volume. Whereas, this is my bottom phase, I will get a small volume. When I come to this, take the center location, then I will get almost equal proportions. When I move down, my top phase volume reduces, bottom phase volume increases. So even though same composition it is having, volume ratio changes, which is very, very useful phenomena which we will exploit as we go down. These are the typical polymers that are used, but most popular is polyethylene glycol and dextran. But dextran is very, very expensive. That's why we carried out research and come out with another one, maltodextrin. That is less expensive, but the problem is it has a high viscosity. Then we move to different salts, potassium phosphate, sodium phosphate, citrates. So many salts are done, but most popular is phosphate, potassium phosphate, because it gives the pH and the environment very close to biological systems. There are several factors that influence the phase formation, that is polymer concentration, its molecular weight. For example, in the previous tie line you have seen, as you move away from the binodal, that is the critical concentration, it is easier to form the two phases, but the problem is Physical properties also change, viscosity will change. So then molecular weight. Higher the PEG molecular weight, smaller quantity is sufficient to form the phase system. So that is advantage as well as disadvantage. Advantage in the sense more amount of water I can have in the phase. But disadvantage is its molecular weight being so high, it itself occupies more space, giving the less free space for the biomolecule to partition. That I will explain in a minute. Effect of temperature, not very strong. It is not a strong function of temperature. And salt type and concentration, these are the neutral salt. Yes, they have a effect on the partitioning. Then if I put a biomolecule in these two systems, it will partition selectively to one of the phases. That's what the meaning of extraction is. Either organic or aqueous, two-phase aqueous. It selectively partitioned to one of the phases. It depends on what? Several parameters like biomolecular size, its concentration, polymers and polymer molecular weight, composition of the phases, system pH, temperature. Each has its own role. So most of the basic work was done by biochemistry people in this area. That's why they also assume that just doing the partition study is sufficient to develop a process. It is not true. Of late, chemical engineers started taking it up and looking at it as a scope for developing a commercially feasible processes for isolation of these biomolecules. So chemical engineers, normally we are not good at the basic sciences. We don't go into the what is the molecular weight, what is the pH, how it affects the structure. So we want everything on a macro measurable scales. So we wanted only single parameter. We want as much as lumped parameters and rationalizing the effect of different parameters into single parameter. One should explain many or all if possible. In that approach, we thought all this partition behavior, effect of all these 4 points I mentioned there into a single parameter called free volume. Free volume means, as the name suggests to some extent, it is the space literally available in a liquid system for the biomolecules to get in. How I measure that? All you know, density. What is density? It is a weight by volume. I reverse that. It is volume available for mass. So I measure the density of the top phase, I measure the density of the bottom phase, and reverse it, I will get volume per unit mass of the top phase and bottom phase. I will know where there is a more free space. If the density of a PEG phase is much lower, of course it is lower, that's why always we refer it as a top phase. So the density is lower, so my biomolecule has a more space in the top phase. So it should partition to the top phase if my hypothesis is correct. You do your experiment and see, yes, it is partitioning to the top phase. Okay. Then I will change the composition and measure these free volumes and see the difference in free volume, top phase free volume minus bottom phase free volume. With that increase, if my partition coefficient is increasing or not. If my hypothesis is correct, it should happen. Yes, it has happened. So we comfortably could explain our partitioning behavior in terms of single parameter called free volume by measuring their density of this phases, which is a far simpler thing. Then it is not easy to have a one solution for all the biomolecules. Each biomolecule is independently has its own characteristics, different. But as I said, again, engineers always looks for a rationality and commonalities. So one common protocol, if I can may propose this, it runs through like this. So I have to make, first step is I have to make a selection whether polymer or polymer salt. Preferably I will go for polymer salt for two reasons. In these aqueous two-phase systems, the density difference between the two phases is very low because 80 to 90% is water. That's why phase separation is an issue. Adding to majority to my issue, the interfacial tension is also low. So already we talked, it forms a emulsion. So that is another issue. So that's why I'll go for a polymer salt system where density difference is higher and interfacial tension is comparable. So emulsion formation will not be problem. Phase demixing after the extraction is easy. Then I will go for the phase diagram already which is reported. Many of the chemistry people, they'll just take two systems, two polymers or two polymer and a salt and do the studies. Develop these binodals. Those data are reported, well reported in the literature, so I need not have to redo it, so I take from the literature. In case if it is not available, we will construct. So I'll take that example also, where we have done for a PEG xanthan system. So then I will go for that. Then phase forming polymer, once I have decided PEG molecular weight, I will vary. So then scan different molecular weights where I am getting a maximum partitioning. Finally, I will go for pH. pH is where my biomolecule is stable. With two stabilities when you are dealing with the biomolecule, we'll talk. pH stability and temperature stability. So here we are dealing with the aqueous ambient temperature. So temperature won't come into picture. We'll never heat the systems because we know that they are heat labile. Then pH will see. Then TLL, that is total phase composition. Finally, volume ratio. Just now I mentioned to you how the volume ratio changes my partition behavior. I will show you in a minute. So first biomolecule which has a immense biomedical applications is phycocyanin. So it is a fluorescence marker. It is a blue pigment, proteinous. It is a protein basically. It has a red fluorescence. So for the veins, they'll put as a tracer and see how the flow is in the blood veins. Suppose somewhere there is a clot, it binds to it and immediately it shows that there is a blood clot here. The advantage, another unique thing about it is, suppose I make a small micro hole and introduce a fiber, optical fiber, and pass light through it and ignite that block, it has the ability to blast that block. That means I can bypass the bypass surgery. I don't have to do a bypass surgery. Just by this I can achieve this. So is it a hypothesis or really true? So we transfer the technology to one of the industry. Incidentally, that industry promoter is a surgeon. He did experiments on rabbit and shared the results back that yes, it is feasible. So, and for cosmetics and food colorants it is used, but not very expensive. See, that's why different purities are gone for different thing. High purity, which will cost me 1 lakh rupees a kg, whereas raw material spirulina is 30 rupees a kg. So that goes for analytical applications, biomedical applications, what I am talking. Lower grade, low purity, crude one will go for food applications. For example, gems, you use the blue color gem coating will be there, that is phycocyanin. Leher Pepsi, one product which was unsuccessfully launched by Pepsi, that was blue. And many of the ice creams will have this, because it's a nutraceutical compound. It's not a food colorant. I consume more for its biomedical value. Nowadays, without even doing this downstream processing, dried spirulina itself in the capsule form, everybody is selling, including Patanjali, they are making a lot of money. So if you look at abroad, like see African countries, everybody grow this in their backlog, small ponds in their backyard. They will just scoop it as a palak and put on the rice and eat. Their constitution is very strong. If I eat like that, I will have dysentery. Even if I take 2 capsules, that itself will be more for my capacity. It is loaded with micronutrients. Very powerful thing. current practice is they use ammonium sulfate precipitation, then do dialysis, then ion exchange chromatography, gel chromatography, all this they will use. Whereas we tried only in a single step of aqueous two-phase extraction. So this is how I was mentioning to you. This is the race course, how it is cultivated. One of the biggest producers is Ballarpur Industries. They have a huge plants in Rajasthan as well as Nanjangud near Mysore. So they approached us for the development of technology. So this is constructed and it is harvested, washed and with the distilled water to remove the adhering nutrients, then homogenize using a high pressure homogenize to break the cells, because my product is inside the cell. Unless I break the cell, I cannot get the product. Then this is under a microscope, you see what is the release of the product. This is a crude extract has come. This crude extract I will subject it to aqueous two-phase extraction, optimize different compositions. Finally, this is where I will play around on the location of the tie line to get my volume ratio. So, suppose the third one I have selected, I got a smaller volume of the top phase where it is partitioning and larger value of bottom phase. Do you think that has an advantage compared to the first case where I have a large top phase and bottom phase? I just want to see how much is the level of mass transfer, how much I am able to convey. Yes, please. And for example, for a moment, you please forget that you are all senior faculties. Assume you are students. Yeah, please. Anybody. In fact, we are all students. As long as we are learning, we are students. Yes, please. Any of you answers, that means I am passed. Otherwise, I am a failure. Because problem lies in the delta C, how it is conveyed. I explained the advantage of volume ratio, that is the most advantageous to play around. Now I am showing a case study of phycocyanin. Compare the third case and first case. Is there any advantage in the third case according to you? If it is not there, you say so, no problem. Yes, ma'am. Do you find anything? I'll go for the youngsters. Yes, he is attempting. Yeah, no negative marks for wrong answer. Please tell.
In third case, mass transfer is high compared to
How do we know mass transfer? Mass transfer is high. Mass transfer will be similar because interfacial tension is same. There is no resistance. What is physically you are seeing? One is coming into a large phase of top phase, one is a small phase of PEG phase.
More space will be available in the top phase if we consider the first case.
Correct. Is it good for me? I am getting my product into a larger volume, whereas I am getting my product in a smaller volume in the third case. Which is better for you? %, I answered. Smaller. Yes.
spaces.
There is no two opinions on that. Why? You complete the answer. You have come near the goal. Why? Because it is a more concentrated form. See, otherwise I have to remove the water either by heating or membrane to concentrate it. Here naturally I am getting a high concentration. See, thermal I cannot think of. Evaporation I cannot rule out because it is a heat level. What is the current method for biomass heat sensitive product concentration? Using membrane processing, say reverse osmosis. That is also not required. Just by properly designing my experiment